In this video, I want to discuss two alternative ways of calculating a p-value in a statistical test. We call the first way a one-sided test, and the other way a two-sided test. First, let's remember exactly what the p-value is. The p stands for probability. It's the probability value. The probability value of what? Well, it's the probability that a particular statistic, or a more extreme value than that statistic, could have come from a null distribution. Why do I keep saying, or more extreme? Let's take a look at this null distribution. What is the statistic here? It's the difference in promotion rates between men and women. Our observed statistic, the real difference in promotion rates between men and women, is 0.3. It's plotted here by the vertical red line. In pink, you can see the area under the curve that is more extreme than the red line. Let's imagine what happens if more men are promoted. The difference between men and women would get bigger, so the observed statistic would become even bigger than 0.3, so we would plot it further to the right. If the red line moves right, the pink area becomes even smaller, as fewer and fewer of the simulated differences are more extreme than it. Let's take a moment to think about what we are actually calculating here. We are calculating the fraction of promoted men minus the fraction of promoted women. Our alternative hypothesis is that more men are promoted than women. In other words, we only care about large positive numbers, where the fraction of promoted men is bigger than the fraction of promoted women. For this specific alternative hypothesis, we don't care about the opposite scenario, those permutations where more women are promoted, and so the statistic is negative. These are extreme values as well, they just lie on the opposite tail of the distribution. But by framing our alternative hypothesis as only calculating the p-value using male-dominated extreme values, we are ignoring that other side of the distribution. So extreme values in this particular experiment are those that lie on the right-hand side of the red observed statistic line. When you calculate the p-value in R, you have to specify which side of the observed statistic to color pink. If you were to specify the left-hand side by accident, you would get a much larger p-value than you were expecting. But let's imagine that we calculated the test statistic the opposite way around. Instead of calculating men minus women, let's calculate women minus men. Remember, our alternative hypothesis hasn't changed. We are still trying to see whether more men are promoted than women. But what will those extreme values look like now? Well, firstly, our observed statistic will be negative 0.3 instead, so it will lie on the opposite side of the distribution. And in permutations where more and more men get promoted, the statistic will become more and more negative rather than positive. So where are our extreme values now? They are on the left-hand side of the red line. We would need to specify the left-hand side when we calculate the p-value in R. Otherwise, we would calculate the wrong p-value again. So remember, for a one-sided test, make sure you calculate the p-value using the correct side of the observed statistic. Now, I have been calling all of these tests one-sided tests. Why? Hopefully you can see why from these pictures. We are calculating the p-value from only one side of the null distribution. We are ignoring the extreme values on the other side of the null distribution. Because our alternative hypothesis says that men are more likely to be promoted than women, we ignore those extreme values of the null distribution where, due to random variation, more women were promoted. But often we want to run a test where we care about an extreme difference on either side of the null distribution. Let's imagine that our alternative hypothesis is no longer that men are more likely to be promoted than women. Let's say instead that our alternative hypothesis is that there is just a difference in rates of promotions between the genders, period. In this phrasing of the alternative hypothesis, we not only care about values of the null distribution in which more men are promoted, which you can see in the shaded pink area on the right, but also about equally extreme values in the opposite direction, in which more women were promoted. In other words, our p-value is now equal to both shaded pink areas. In other words, we have exactly the same data in our null distribution, but merely by changing how we state our alternative hypothesis, we have doubled the size of our p-value. This is a two-sided test because now we are calculating our p-value using the extreme values from two sides of the null distribution. Let's take a look at one- and two-sided tests side by side. Here I have run the same gender promotion data through both a one-sided and a two-sided test. In the one-sided test, which you see on the left, the p-value is below 0.05, so we can accept our alternative hypothesis that men are promoted at higher rates than women. In the two-sided test, the p-value doubles because the pink shaded area is twice as large. The p-value is now larger than alpha, so we fail to reject our alternative hypothesis. This example illustrates a great point about the difference between these two types of tests. Two-sided tests are much more conservative. Because the p-value is twice as large, we are always more likely to fail to reject the null hypothesis. I'll end this video with a cautionary warning about hypothesis tests. Typically as scientists, we want to accept our alternative hypothesis, so we want as low a p-value as possible that lies below the alpha value of 0.05. One-sided tests should only be used when there is a good reason to think that the data might only occur on one side of the distribution. We should also always specify the type of test that we are going to use in advance of our experiment. And we should never ever switch to a one-sided test after collecting the data just so that we can lower our p-value to a point where it is considered significant.